and hopefully that shows you where we've come and what you should be able to do. Okay, right. Okay, just checking chat, everything's all right. Just a recap then. So we've been looking at, we're going to look rather at distance and time graphs now. Okay, the distance time graph is to always make sure, and with speed time graph, is that you check, always check to see what's on the axes. Okay, now obviously distance time graphs are really useful because we can visualize what's going on, and we can also use them to calculate speed. Always have a look, what story does the graph tell? What tends to happen in O-levels, and as an examiner, GCSEs and international GCSEs, I see that a lot, that people get very confused between speed time or velocity time and distance time graphs. So always take a minute to look at the axes first and say, well, time's moving on, so what's increasing or decreasing as time is moving on? Well, in this case, obviously, it's the distance. So I know right away I've got a distance time graph. So from this, we can see that it goes to the origin. And we can see that when the as one increases, the other increases with it. So we can see that it's a proportional relationship. How do we calculate the speed? Okay, so how can we calculate the speed from that? Well, you may know this from maths, but we can use it by calculating the gradient. Okay, so we're going to find the gradient to find the speed. Okay, so how do we do that on a real graph? Well, what we do is we calculate the change in the distance for the section that we're interested in and divide it by the change in the time. How does this give us the gradient? Well, we know, well, we know that speed is distance over time. I'm going to put V for now. Okay, so we know that speed is distance over time. And we also know that the gradient of a graph is the change in distance. I'm just going to use a little symbol delta to mean a changing. Okay, so it's a change in the y values. I'm just doing that. So strictly speaking, it's a change in the y values divided by the change in the x values. You may know it as rise over run. Okay, or just change in the y values divided by change in the x. So the little symbol delta, that's all that means, to save me having to write it out. And so we can see that if we calculate the gradient of this graph, it actually means something, because the change in the y values is the change in the distance. So it's the distance we've travelled. And the change in the x values is the time it's taken to travel that distance. And so the gradient of a distance time graph gives us a speed. Okay, what else does this tell us? Okay, so we go back to this distance time graph. What else does it tell us? Well, it tells us, if we look at that graph, you can see that the gradient is constant. And so that tells us that we've got a uniform speed. It's the same. It's not changing. So if you see a straight line on velocity or speed time graphs or distance time graphs, it tells you that the quantity isn't changing. Curviness means change. Straight line means uniform or constant. So we've got a constant speed, and we can obviously determine that by calculating the gradient. Would anyone like to work out what that speed is? Okay, so remember, speed is the distance divided by the time. And if you want to type it into chat, that will be fantastic. So remember, we're looking at the gradient, so we can look at the change in our y values, which is the distance. So that is 50 meters. Excuse my writing there. And yes, it's a distance per unit. Well done. Okay, and the time's 100 seconds. Brilliant. And so the time is 0.5, as I've got that in chat now. Okay, 0.5 meters per second. Okay, fantastic. Okay, so we can see that exactly why the gradient gives us a speed, because we're just calculating distance over time. Okay, out of these three then, we can see we've got three uniform speeds. The speed's constant, it's not changing within each line, but the slopes are different. So which one of those lines is going to be fastest then? Well, you can probably tell straight away, but bear in mind, if you ever get confused, the red one, it is the red one. But if you ever get confused, remember you're looking for the steepest gradient. So the steepest gradient there is the red line, and so that means that that constant speed is the highest of the three. I won't ask you to calculate it. So the steeper the gradient, the biggest speed. So what is a horizontal line? Well, remember I said always follow the story. Okay, so what does the graph tell you? Well, this graph tells me that as time is ticking on, as time does, the distance is staying the same. And time moving on and distance staying the same is a rather fancy way of saying that the thing is stationary or it's stopped. So its distance away from its starting point has stayed the same. And so, yeah, okay, so it's stopped moving, 0 speed, well done. So what we've been looking at up till now is just constant or uniform speed. Obviously, if we see a curve, then we know that the speed is changing and we've got a non-uniform speed. So if it's linear, then the speed is constant. Okay, so this is a little bit of information I pasted up for you. So this is from Usain Bolt. Now, don't know very much about sport, but he did a world record or something. I think it was... Anyway, but this is his speed time graph, okay? So distance time graph rather. And so you can see that at the beginning of the race, we've got this curve going on. So that tells us that although the speed is increasing, because if we took the gradient at this point and then took the gradient here and took the gradient here and then took a small gradient here, you'd be able to see that the speed is increasing. So it's actually there's acceleration going on there. And because the speed isn't uniform, that's why we've got this curve, okay, because the gradient is changing. However, once we get up to top speed, then the speed is uniform, so that's why you've got that constant, that straight line bit. Okay. So as soon as you see a curve on a distance time graph, then you know that the speed is changing. And of course, another word for change in speed divided by the time is acceleration. Okay, everyone all right with the distance time graphs? I've got a bit of a straightforward question here that you might want to have a look at some of it. Oh, this one's not coming up, so I'm just going to get rid of that. I'll share screen. Okay. Okay, so this is a bicycle ride. Okay, now Reg isn't here now, so she can't enjoy this. But Reg and I went cycling one day, not likely, and there's the distance time graph. Okay, not likely when you see the distances involved. Okay, and so what we can do is with this very neatly can tell us the story of our whole day out. So what's happening in the first part then? Well, first of all, how far did we travel in total? Anyone got an answer for that? 1.5 kilometres. Oh, right. No, I think we probably travelled a bit further than that. Do you need me to zoom in? 50. Okay, so we know we travelled 50 kilometres in total because obviously this is where it ends. How long were we cycling? Oh, don't worry. How long were we cycling for? That's how we learn, okay? Am I making mistakes? Yeah, so we were cycling for 6 hours. However, we did have a bit of a long lunch break in between. I suppose we were out of the house for 6 hours. Now, if we wanted to calculate the average speed for the whole ride, then we'd obviously do the total distance divided by the total time. Now, that's not going to give us a very high average speed. Why not? Yes, 50 divided by 6. So why is that not going to give us a very high average? So I'm just moving some of my things out of the way. Well, if you look in the middle, you'll see that we actually stopped. Okay, so we actually stopped for, 2 hours for lunch. Yes, absolutely. And so that's why our average, it should come out at 8.3 kilometres per hour. So, okay, so let's do speed is distance over time. So that's 50 kilometres. In fact, let me write on this. Okay, so 50 kilometres, I don't know, there's a bit of delay on the whiteboard now, so my writing's not as neat as it normally, well actually it's never neat, but there you go. Over six hours, okay, so that tells us it's 8.3 kilometres per hour. Okay, right, so just by looking at that, which you can see that we travelled at a constant speed, we were travelling at a constant speed twice, but one of them, or uniform speed, one of the uniform speed was faster than the other. Which one was it? Between two which points? Okay, anyone else? So between which 2 points were we travelling the fastest? Fantastic. Okay, C to D. And how can we tell this from the graph? Great. Okay. Sorry, I was a bit quick there. So how can we track? Well done. Okay, those of you that are answering from the steeper gradients, good, fantastic, well done. How long did we stop for lunch? Well, I think that that's pretty obvious now. We stopped for 2 hours. Yes, I know it's a very long lunch break. Okay, 2 hours. And what you could do is calculate the speeds between points A and B, if you okay, and C and D. So if anyone wants to have a go at those, if you can see it well enough. Okay, if you need me to zoom in. Yeah. Okay, watch out for the units. Remember, have a look, see what units are on the y-axis and what units are on the x-axis. Okay, yeah, so 10 kilometres per hour for the first one. Well done. And what about, oh, I've got something unmuted, okay. Kilometres per hour, well done. Okay, and what about the next bit between A and B? C and D, rather. Okay. I'm going to put that in. Well done for the person from Amar, who's put that in. Do apologise if I'm pronouncing names incorrectly. I will learn them for next time. Okay, and so that is going to be 20 kilometres per hour. Good. So we can see that speed time graphs are actually quite useful. Now, I'm going to have a quick look. So we'll make a start on velocity time graphs. Sorry, just speed time graphs. So this is a distance time graph. We're going to have a look at speed time graphs now. Okay. But just a quick overview, and we'll save the questions for most of the questions for next time. Now, just as a recap, we know that speed is distance divided by time, and the difference between velocity and speed is that velocity is a vector quantity, so we need to know the direction. Okay, and that is why when we were calculating acceleration before, it was possible to have a negative acceleration because it depends on whether we're going and increasing or decreasing. So strictly speaking, if something's coming back towards us, then we would say the velocity is changing, okay, to -3 meters per second. However, I just want to go back to this. Okay, let me just move on. We can do this. Okay, let's do this acceleration question then. Okay, so acceleration is the change in velocity over the time taken. So we'll just do this one. We've talked about why it's measured in meters per second squared. And so if you just quickly, just to recap what you've done before, do you want to calculate the acceleration of that car? Okay, so 5 to 25 in 4 seconds. Okay, I've got some answers coming in now. Good, and you remembered, well done. You remembered the, Emma, you remembered the units, correct? Okay. Okay, all right, well, let's go through that. So the change, sorry, that should be 25 to 20 in 4 seconds. So what's our change in speed? Well, it's 20 meters per second, and the time is 4. Okay, so it's 5 meters per second, which is 5 meters per second squared. Great. So I'm just going to go through that. We'll do that another time. What I wanted to do was very quickly introduce velocity time graphs, sometimes called speed time graphs. Okay, we don't usually make such a big distinction at GCSE level. At A level we do, and so we can talk about them interchangeably as speed time graphs. And this time we wanted to try and figure out why the gradient or the slope represents the acceleration. Well, if you think about it, there you've got a high acceleration, a low acceleration, and a 0 acceleration. So remember that always look at the axes. So what does this tell us? As time's moving on, in this case, the velocity is staying the same, or the speed is staying the same. So that tells us we've got a constant or uniform speed or velocity. Okay. I noticed that some books and some use constant, others use uniform. It means exactly the same. Now, why does the slope give you the acceleration? Well, it's exactly the same argument as before. If the acceleration is the change in y values divided by the change in x values for the gradient, okay, so our change in y value is the change in velocity. I'm just going to put delta to represent a change in. So that's our change in speed or change in velocity. We use the terms interchangeably in at GCSE for this particular topic. And then we're going to talk about the change in the time. And we know that the change in speed divided by the change in time is the acceleration. And so that is why the slope or gradient of a speed time graph, sorry, can't quite get that on, gives us the acceleration. Okay, straightforward. A lot of the time when you calculate gradients in maths, you're just calculating a gradient as an exercise, but in physics they actually represent real things. And so that's, you can see we're dividing meters per second by second, and so we've got acceleration. Okay. Now, if it's going downwards, well, what does this tell us? Remember, read the axes. Well, it tells us that as time is moving on, as time tends to do, which is moving on for us, so I'm going to have to wind up soon. As time is moving on, then what's happening to the velocity, to the speed? Well, it's actually decreasing. So this is what we call a negative acceleration. If you calculate that gradient, you'll come out with a negative number. And if you remember from before, and when we looked at the syllabus statements, another word for a negative acceleration is a deceleration. Either is acceptable, but if you're doing the calculation, put the minus sign in, and then have a look to see whether it's asked you for a deceleration or not. Okay, so just to peek ahead to next time we're going to have a look at how the area represents the distance travelled, and we're going to use speed time graphs or velocity time graphs in order to calculate distance. And we're going to have a look at more complicated graphs as well that show how the acceleration is changing. The key thing I want you to take away today from speed time graphs or velocity time graphs is that so far we've looked at straight lines. Okay, so that tells us that the acceleration is constant, it's uniform. Remember what I said before with the distance time graph, it's exactly the same with the speed time graph. If you have a curve, then you have a non-uniform acceleration. So for example, let's say a car accelerated for the first second at 10 meters per second, and then in a second, the next time interval, it increased its acceleration, then we could say that over that total time interval, the acceleration is not constant, it's changing. And next time that will lead us very nicely into what happens when objects are falling under gravity. So I hope that you enjoyed this session and that you found it useful. To recap, then today we have looked at distance, we've looked at calculating speed, we've looked at the difference between average speed and instantaneous speed. You should also be familiar with the term, I'm sorry, I forgot what I was saying then, excuse me, you should also be familiar with the term uniform speed or constant speed, that's what I meant. And you can also calculate, hopefully, accelerations and speeds and rearrange equations to get for those higher level exam questions. We've also had a look at distance time graphs, and hopefully you should be able to summarize the key features of a distance time graph and use it to calculate the speed. And we've had an introductory look at speed time graphs, sometimes called velocity time graphs. I'll explain more about that next time. And we've had a look at the difference between a uniform acceleration, where we've got a straight line on a speed time or velocity time graph, and a curving line. Remember, curved line always means that something's changing. So I hope you found it useful, and I look forward to seeing you next time. Before we finish, has anyone got any questions? Okay, I'm just going to, because there are just a few of us, I'm just going to say goodbye then. If you have got any questions, you can always, that you come across later, thank you very much for that. You can always contact me at 4D eLearning if there is something that you're not sure about. You're very welcome. Bye-bye. Bye-bye, Aisha. You're very welcome as well. Okay, hope to see you next time. Goodbye.